All right, I want to spend just a few minutes talking about energy conditions, and then we're going to move on to gravitational path integrals. So what's an energy condition? Well, there's a very long history of trying to understand what it means for energy to be positive in general relativity. Roughly speaking, we expect energy density to be positive in some sense. Okay, but we need something that's covariant. We can't write it this way, and we need something that's true. And so there's a very long history of this, especially because a lot of the basic theorems and facts about general relativity that people often state as true rely on energy conditions. So like the statement that black holes have a singularity, even in generic situations away from Schwarzschild, that relies on an energy condition. The statement that there's a Big Bang, that relies on an energy condition. And so I just want to kind of say a few words about this. So for this discussion, I'm going to take V to be a forward time-like vector, and K a forward pointing null vector. So we already discussed briefly the strong energy condition. Strong energy condition, SEC, because this came up in our discussion of focusing in the Raychaudhuri equation. So remember, this was T alpha beta minus a half T G alpha beta V alpha V beta is non-negative. And if you go to the Einstein equation, then this is the same as saying that Ricci dotted into this time-like vector is non-negative. And as I said there, well, there are situations where this might be true, but it's certainly not true in general. It's violated by a positive cosmological constant. If for some reason you don't like the cosmological constant, then it's also just violated by a positive energy density from a scalar field. So there's really no way avoiding this. If you have a scalar field with a potential and you turn that on a little bit, that's going to act like a cosmological constant. So it's just not true in general. This is violated, for example, by a positive CC. Okay, so the next one that people like to talk about is called the weak energy condition, WEC. So the weak energy condition is, well, it's just a covariant version of this energy density condition. The covariant version of this is T alpha beta, V alpha V beta is non-negative. So that is any observer who moves on a time-like world line should detect a non-negative energy density. Is the question?
Yeah. So historically, did people believe the strong energy condition like before the universe was observed to be expanding?
I don't know. I think the strong one actually is, the weak one is, I think the strong one is pretty easy to violate. Like I was saying, you could do it with a scalar field. So like GR coupled to a scalar, I don't see how you could think that this was true, but I don't know historically. The weak energy condition at least sounds a little more intuitive to me, but it's also false. So this is the energy density according to an observer moving on this world line with velocity v. Maybe I should mention that the strong energy condition does not imply the weak energy condition. This is a general feature of theorems in GR that the strong one often does not imply the weak one. There's also cosmic censorship has this. There's strong cosmic censorship and weak cosmic censorship, which which have the same property. But anyway, this one is also violated. It's pretty obviously violated by a negative cosmological constant. And it's also violated by something like Casimir energy. So again, good for proving theorems, but not good for being true. Now I'm going to get to the most interesting one, which is the null energy condition, the neck. So the neck states that T alpha beta n alpha, did I call it n? K. So dotted into a null vector, k alpha, k beta, is non-negative. So this one is almost true. I can give a little bit of intuition for this. Okay, so positive CC. So the cosmological constant shows up in T mu nu as something proportional to G mu nu. Okay, so by dotting into a null vector, the cosmological constant drops out. Okay, so constant energy densities drop out of the null energy condition, and that's why you can hope to have something that's true. So constant energy densities drop out, so neither sign of the cosmological constant is going to cause a problem. It's not quite true. It's violated by quantum effects. So it's violated at order h bar in any quantum field theory. Actually, we've already seen this. I don't remember if I mentioned it, but we've already seen this implicitly because we showed that under the null energy condition, null rays focus and give us the area theorem that the area of the black hole has to increase. But with Hawking radiation, it doesn't matter what kind of quantum field theory you have. Any quantum field theory on a black hole will lead to Hawking radiation, and Hawking radiation will cause the black hole area to decrease. So we already know that it violates the null energy condition. And you can calculate that and see that in much more detail. So for example, Hawking radiation. I'm going to now just say a few words about positive energy in quantum field theory. And in particular, I'm going to prove to you that this is violated. I mean, there's a very nice and easy proof that this is violated in any quantum field theory. It's a deep and general fact about quantum fields that there's no such thing as a local energy condition. There's no inequality that you can write on the stress tensor that's true. So, of course, in quantum theory, the Hamiltonian is bounded below, and we can shift it and say that the Hamiltonian is non-negative. But this is the integral over all of space of the energy density. And when I say, so the statement is that Q of t does not satisfy any local energy condition. And I'm going to prove this for you. I'm going to prove it for T00, but there's a general argument. It's just easier for me to write it this way. Proof for T00. So first of all, the expectation value of T00 of x in the vacuum has to be 0 by Poincare invariance. However, the 2-point function of T is not 0. You can check this in your favorite quantum field theory, but it's also something that can be understood more generally, just because, well, basically, if you think of the quantum state that you get by acting on the vacuum with T, that is not allowed to be 0. That has to be a local operator like this cannot annihilate the vacuum state. So that quantum state can't have 0 norm. Okay, so now let's let 1, the state 1, be T00 of y acting on vacuum. And then what we're going to do is we're going to calculate T00 of x in the 2x2 subspace. I and j run over the vacuum state and this state 1 that we just defined. Okay, so this is a 2x2 matrix. 0, 1, 0, 1. And what we just showed is that this element is 0, because that's the expectation value of the energy of T00 in vacuum. This guy here is the 2-point function. Let's call that A. Actually, I'm going to call it B, because that's what I got to say. Then this one is just B conjugate. And this third one here is something. This last one is something, so I'll just call that A. And the point is that this is not a positive matrix. Calculate the eigenvalues of this matrix, then one is positive and one is negative. Therefore, you can find a state in this in the span of these two in which T00 has a negative expectation value. So this implies that there exists a state V with V T00 of x be negative. And that's it. So quantum field theory just can't have any local energy conditions. What's going on here is that well, this has to do with the highly entangled nature of the quantum field theory vacuum. Okay, so the fact that the key fact here was that you cannot annihilate the vacuum by hitting it with a local operator. And the reason you can't annihilate the vacuum by hitting it with a local operator is because of the entanglement, which we can see from equations like this, because this encodes correlations at space-like separation, which are coming from entanglement at space-like separation. Okay. The same argument applies to the energy of any finite region in, is there a question? Yeah.
I'm confused. So the vacuum is not the lowest energy state?
Well, the vacuum, yeah, that's right. Well, this is not the energy, this is the energy density. The vacuum is the lowest energy state, but what we've done is we've found a state with some negative energy density somewhere. The total energy in the state 1 will be positive. In other words, you have a little bit of negative energy somewhere, but it's going to be made up somewhere else with even more positive energy.
Sorry, how does this imply that UFT does not satisfy any local?
Well, I didn't prove the general statement that it doesn't satisfy any local energy condition. I just proved that T00 in any T00 can always go negative, but there's a more general argument that there can't be any local energy conditions. And that includes, like, we said that integrating T00 over all of space, that's the energy, and that can be bounded below. But if I replace this by any bounded region, then even if it's huge, then the same argument applies. So when I say local energy condition, really the energy in any bounded region can go negative.
You mean the total energy in that bounded region, or the energy at one point somewhere in the bounded region?
The total energy of a bounded region can go negative. Now you could ask whether you have to integrate over all of space to get the total energy, or whether you can do something kind of in between, like something that's infinitely large. So it needs, if you have an energy condition, it needs to go to infinity. So it needs to not be a bounded region. But it doesn't necessarily have to be all of space. It could just be some infinite region. And so you could ask whether there are any true energy conditions of that form. And there probably is one. Okay, so the ANET stands for the averaged null energy condition. So the average null energy condition states that integral dn alpha t alpha beta and beta is non-negative. And what this integral, so n here is a null vector. So this is the integral of the null energy over a null ray. So integral of the null energy over a null ray. There's one more caveat here. It has to be an achronal null ray. Okay, so you integrate over an achronal null ray. An achronal null ray is one where you can't take any shortcuts. So there is no time-like path between any point on the null ray and any other point on the null ray. So like this line in Minkowski, that's an achronal null ray, but the photon orbit around a Schwarzschild black hole is a chronal null ray, because it loops back and you can take shortcuts along time-like paths. Okay, so I think it's probably true in general in quantum field theory coupled to general relativity that that the stress tensor integrated over achronal null rays has to be positive. This hasn't been entirely proved. But it's, let me say, probably true, and has been proved in Minkowski. So in other words, if we forget about gravity and curved space for a moment, and just talk about quantum field theory and Minkowski, ordinary quantum field theory, then this is already a non-trivial fact about, or non-trivial claim about ordinary quantum field theories. And that's been pretty much proved. I put it in quotes just because proofs always come with assumptions, and we're not doing math. Okay, yeah.
It's also been proved similarly in like a lot of other spacetimes too, like AS2 cross S2, right? Like in the
Yeah.
last couple of years.
Yeah, they're, as far as I know, they're all conformal to flat space. Yeah. Was there another question?
I was just going to ask why you put proved in quotes, but then you said it.
Oh, okay, yeah.
What's the intuition for why this should be true? Like, I was with you when you said, when you were talking about the null, or what was the one before this? Just like how in quantum field theories, you can have like some negative energy density over here, but it has to be made up for. But what is like integrating over the null vector doing for you?
There are some versions of this where, for the general statement, like I don't have great intuition. Well, I can give some partial intuition for it. So one thing I can give intuition for is if you take Minkowski. So this is Scri plus in Minkowski space, and if you put your null ray up here, like that, then this is an observable. This is the amount of energy deposited in a calorimeter in an experiment that lasted forever. And so we don't expect to look at the calorimeter at the end of the experiment and see a negative number. Now you might be a little bothered by seeing a negative number temporarily even in your calorimeter, but the excuse for that is that there's, and this is vague, but that there's some kind of energy time uncertainty principle where if you don't integrate forever, you can't be sure that it's going to be positive. That's one piece of intuition. I think that's the best one. I think that's the best one that I can give easily. This is called the conformal collider point of view after Hoffman and Malsena.
But that's just
But-
one atonal null.
You mean this one sitting up at infinity?
Yeah.
Yeah, and if it were a conformal field theory, I could move that anywhere. But in a non-conformal theory, I can't do that. So I don't know. I don't have a good explanation. No, historically, the way this happened is that people just wrote down like lots of different ones, and they didn't know which ones were true, and this was like the last one standing, because it's not that hard to disprove the others, because how would you do this? Well, if you're doing, you just take your favorite quantum field theory, say it's a free field in 4 dimensions, free scalar. Take a free scalar. Then you just write down the stress tensor as a sum over modes. Sorry, that's the field. Write down the field as a sum of modes, and then the stress tensor T mu nu is some normal ordered product of derivatives of phi, and it's the normal ordering that gets you. Okay, so in classical mechanics, if in classical theory, T mu nu is basically, well, if you take T00, for example, it's going to be dt of phi squared, so that's why it's going to be positive. But it's the normal ordering that gets you, and so this is not the square of anything. Even T00 here is not the square of anything. But what happens is when you integrate over null ray, it kills the normal ordering terms, and then the classical intuition becomes true. So that's one way to see it. Other questions?
So you said that in any bounded region you could make the energy, the integrated energy negative, right?
Yeah.
So that means that the vacuum better only be globally defined, and there's no sense in which there's like a vacuum in subregion.
Yeah, that's right. Yeah, the vacuum really has it has correlations everywhere. You can't really talk about it first. I mean, you can talk about the reduced density matrix of vacuum in some region, but the full vacuum is everywhere. Okay, I just wanted to sketch some of that. We're not really going to use this, but you know, for the particle physicists, cosmologists in the audience, if at some point in the future you hear someone talking about bouncing universes, then you should ask them whether the achronal ANEC is satisfied in their model. It's probably not, and you know, we should worry about this because these are you can't just do any old thing with a quantum field theory, even though the energy can go negative. You can't just do any old thing. And bounds like this are pretty strong on things like bouncing cosmologies.
But the ANEC is just something that we guessed was true, so what would go wrong if it was violated?
Well, now there are proofs of it. What would go wrong? You can look at the proofs and see what would go wrong. One of the proofs is monotonicity of relative entropy. Okay, so if that was wrong, then you'd have a real problem because that's guaranteed by unitarity. The other proof is causality. So basically, this thing would lead to time advances.
But you just said it was not proved in general, so those things sound like proofs to me.
Well, those proofs are Minkowski.
So what if you had some like bouncy universe that wasn't Minkowski?
Well, yeah, no, I agree. Then it's not proof that the achronal ANEC will always hold. But I would be suspicious of any situation where it's claimed to be violated and want to check it very carefully because I don't know of any case where it's believed to be true. And yeah, that's all I meant to say. Okay. New topic. Gravitational path integrals. We spent several lectures talking about and reviewing the situation with path integrals in quantum field theory. For all of that discussion, there was no gravity. Okay, there was curved space, like I was drawing funny manifolds and stuff, but the curved space was not fluctuating. There was some fixed curved space, and we were doing quantum field theory on that fixed curved space. Now we want to include the fluctuation of geometry. So in Q of t, I'm going to start by just saying what's different here. So in Q of t, when we do a path integral, z is the integral d phi of this is a Euclidean path integral. We could make a Lorentzian path integral. The Euclidean path integral is the integral, and remember, I'm using phi to denote all fields except for the metric g mu nu. For example, we talked about how the thermal partition function defined to be trace of e to the minus beta h, is equal to the path integral that we've been drawing as this cartoon. That is, it's a path integral on this cylinder, which as an actual equation, this is the path integral d phi with the boundary condition that phi of tau plus beta is equal to phi of tau of e to the minus Euclidean action. Okay, so that's just what we talked about before. Quantum field theory, we pick a manifold, like the cylinder, then we integrate over quantum fields on that manifold. In gravity, of course, we also need to sum over the geometry itself. So in quantum gravity, the path integral z is, I'm going to put this in quotes, integral dg d phi e to the minus Euclidean action of g and phi, where g is the metric. Now, I put this in quotes because we can't do this integral, of course, and because gravity is not renormalizable. We don't literally think that quantum gravity consists of coupling matter fields to a metric and then integrating over them. That's just not quite right. It's right at low energies, so this is the correct effective theory at low energies, but this theory is not renormalizable, and how that'll show up in practice is if you try to do this path integral, you can't really make sense of doing this integral. You can't literally do this integral. We will nonetheless spend the rest of the course doing this integral. Okay, so how do we do that? Well, we don't specify the manifold. Well, the question I want to address first is what do we integrate over? Like, what manifolds do we integrate over? For example, if we want to talk about the thermal state, in quantum field theory, we said we should do it on a cylinder. Well, now what? We're supposed to integrate over the manifold. And the point is that we don't specify the manifold, but we do set the boundary conditions. And this is going to be key. So
Tom,
yeah.
how am I supposed to interpret the wick rotation from the Euclidean to the Euclidean from the Lorentzian path integral?
So are you talking about for gravity or?
Gravity, yeah. Because these are now like fields on like a Euclidean space-time.
The wick rotation is similar in that we're going to have the same kind of, well, I'm jumping ahead here, but it's going to be similar in that Euclidean path integrals prepare states. Now they're states in quantum gravity as opposed to just in quantum field theory. But again, Euclidean path integrals will prepare states, and Lorentzian path integrals will evolve them in time. But there are some crucial differences which I'm coming to.
How does having gravity not let you specify the manifold?
Well, because G mu nu is the field now, and we're supposed to do a path integral over the field. But that's the geometry. Okay, so we're integrating over geometries, and we can't very well fix the geometry and then integrate over the geometries. Now, you might ask if we could fix the topology or something like that, and then integrate over metrics on that topology. That also seems to be wrong, but for more subtle reasons that we'll come to. Yeah.
Wait, why? I think I'm confused with what the problem is. Why is it an issue that we're not specifying the manifold? Like, aren't we just doing the same thing we do in normal quantum field theory, where we set the boundary conditions and then let the field, you know, integrate over all the field configurations in the middle? Isn't it the same?
Yeah, that's what we're doing. Yeah.
Okay.
I'm just making a distinction.
Okay.
Yes, that is what we're doing. But those boundary conditions are going to be, yeah, that's what we're doing.
Okay.
Yeah.
Do we have to worry about, like, for some of the manifolds that are included in this integral, the coordinates won't be good anymore? Like, are we kind of using fixed coordinates in the action?
No. Well, when we actually go and do a calculation with Feynman diagrams and stuff, we're probably going to end up picking a coordinate system. But then we have to be very careful about all the gauge fixing and all that stuff and make sure that it's not coordinate dependent at the end. But in principle, this is a totally covariant geometric thing that we're doing. The action is coordinate invariant, and we're going to integrate over manifolds, really.
Okay, but when we do this in practice, we would often like write the action as some like integral d4x with a square root det g in there, and maybe x isn't a good coordinate for all of the geometries. Maybe.
Yeah, we will have to be careful about that. Yes, we will have to be careful about that. So for example, what about the thermal trace, z of beta? So in quantum field theory, we said that z of beta, we showed that z of beta was the path integral on the cylinder. Let me write this up here because this is going to take a board. So in quantum gravity, we say that z of beta is the path integral over metric and fields subject to the boundary condition that it's asymptotically a cylinder. So in quantum field theory, we did the path integral on a cylinder. In quantum gravity, we do the path integral on manifolds that are asymptotically a cylinder. So the boundary condition is that ds squared near infinity should be approximately d tau squared plus dx squared plus subleading with tau is identified with tau plus beta.
What do you mean by infinity?
I mean that there's a place where the metric looks like this, and then we're going to have to worry about how big the subleading terms can be. And I think it's better for us to just postpone that for the examples. But the idea is that we specify the asymptotics of some manifold, and then let gravity fill it in. Okay, so in words, we're saying that the boundary condition is that this is asymptotically a cylinder of proper size beta. Now, I warn you that my notation for my cartoons for doing path integrals are just cartoons. It's not exactly like standard notation or anything. And now when I talk about gravitational path integrals, it's going to get even worse. But if we're going to draw this as a pattern, if we're going to draw a cartoon for this, which is going to be really helpful later, then I would say that in gravity, well, let's put them side by side. So in Q of t, z of beta is the path integral on the cylinder of size beta. In gravity, z of beta is the path integral on a manifold, which asymptotically is a cylinder of size beta. But we don't get to say what it is anywhere else, because that's what we're integrating over. I can't draw a picture of it. We're doing the integral over all of the ways of filling in these asymptotics. Was there a question?
Yeah. How do you know that it's correct to specify the boundary conditions this way?
I'm coming to that in one second.
Okay.
Okay, so this cartoon, which nobody draws this, but this cartoon represents this whole set of words on the other board. This is the integral over metrics and fields, Euclidean action, subject to the boundary condition that you have an asymptotic cylinder of size beta. That set of words is captured by this cartoon. Okay. Usually when people draw these pictures, they just draw the saddle point. What we're going to see is that there's a saddle point that dominates this, and usually people will just draw that saddle point so they don't have to draw this funny question mark. Now, there's an important difference, which is subtle, but very important. And we'll discuss this more as we go, but I want to get it right out there from the beginning, which is that in Q of t, we derived the claim that trace of e to the minus beta h, that is summing over states, doing the trace over the Hilbert space, summing over states, is equal to this path integral on the cylinder. We derived that. We spent a lot of time deriving the relationship between the operator formalism and path integral formalism. We chopped up these path integrals and inserted states and stuff. We derived this formula. In gravity, this is a postulate. Or it's a guess. Let's say an educated guess. It's a hypothesis. We do not derive this fact. So somebody asked me how we know this is the right thing to do. We just make it up. It's a made-up hypothesis, and you cannot derive it from the kinds of cutting of the path integral insertion of states that we talked about in quantum field theory. We guess this formula, and then we check that it gives us reasonable answers. Okay. There isn't really anything else you could. I mean, I'm not giving it quite enough credit. There isn't really anything else reasonable. So you can give up on the path integral, or you can accept that this is the way to proceed. But what we want to do is we want to take this as an assumption and see where it leads us, and it's going to take us somewhere interesting and consistent. Okay. Now, how do we actually do these? Calculations? So, well, I said we don't know how to do or even define the gravitational path integral. So, what am I talking about? Well, the answer is that we work in a semi-classical approximation. So the semi-classical approximation means that we're just going to suppose that this integral is accurately captured by the extrema of the exponent. Okay, there are many cases where we know that this would be true, like in Lorentzian signature. If you have a integral like this, you can use stationary phase, steepest descent, etc. That's motivating the equation that I'm about to write, but it's just motivational. Because like I said, this integral doesn't even make sense. If you try to write it down and do it, not only is it not normalizable, there are wrong sign terms up here. Like it doesn't really make sense as an integral. But what we're going to do is we're going to nonetheless use the semi-classical approximation. That is, approximate this by a sum over saddle points of e to the minus the action on the saddle point. So the bars here indicate a classical solution. So we solve the classical equations, we plug them in, and calculate the on-shell, so we find some on-shell configuration. We plug it in, we calculate the on-shell action, and that gives us a leading approximation. But we can also include corrections to this by incorporating the fluctuations of the quantum fields so we expand the quantum fields around G bar and phi bar, and we expand in those fluctuations, and we can calculate order by order corrections around any given classical solution. The first term here is order 1 over G Newton, because the gravitational action comes with that 1 over G Newton up front. The second term would come from one loop quantum effects, and that second term is order G Newton to the 0, and so on. You can calculate corrections order by order in G Newton that come from quantum corrections. Okay. I guess I should mention that I'm calling them saddle points. That's what everyone calls them, but they're really just classical solutions. Whether this is a saddle point or an extremum or a minimum or a maximum, etc., kind of depends on whether you're in Lorentzian or Euclidean, and I'm just going to always call them saddle points. Yeah.
If we were doing a Lorentzian path integral instead, could we like specify the geometry in like the past and the future, like infinite past and infinite future, and integrate over geometries in between, and that would give us some like matrix element for going from that geometry to the other geometry or something?
Yeah, it's similar in that way.
And that's also just an assumption.
Well, okay. What part of this is an assumption? Let's go back to that. Okay. These corrections here, and even the leading term, like this is the only sensible way to try to do quantum field theory when coupled to gravity. So I wouldn't really call that an assumption exactly. You know, we don't have a UV complete theory, and we can't fully make sense of the path integral, but this is just the right way to do quantum mechanics when coupled to gravity. There's a couple things here, though, that I'll call an assumption. One is the claim that to get finite temperature, you should use an asymptotic cylinder. Okay, because we know how to get finite temperature. You're supposed to take trace e to the minus beta h. That's the definition of finite temperature. And we are not going to go from that definition to this path integral. Okay, so that's an assumption. And the other assumption is that it makes sense to sum over saddle points. And this is rather subtle, because if you've done any really hard stationary phase or steepest descent calculations, you know that there are rules about how to include saddle points to calculate an integral. You don't just willy-nilly include every saddle point you like. You have to deform the contour and think about Stokes lines and anti-Stokes lines and things like that. And there's no procedure to do that because we don't know how to define the starting integral. Now, in principle, if you give me an integral, I know how to apply all that Stokes business and get to a stationary phase approximation. But if you give me an integral that's not even defined, then I just have to do my best to guess what the semi-classical approximation is. So that step is sort of an assumption, I would say. I mean, it's a reasonable assumption. We're gonna make sense of it, and it works really well. I just want to be clear that we're not exactly like starting from traces in Hilbert space and working our way from there.
But you could make similar statements about unitary evolution and Lorentzian, correct?
Yeah, I think there's a lot of similar statements there. Yeah.
For fixed topology, why is the integral not defined?
Well, doing the path integral is the same as calculating everything in the quantum theory, and it's not renormalizable. So we know that's impossible.
It's that sense.
But
It's only that sense.
well, there's actually it's slightly worse in gravity. So in quantum field theory, when you go to Euclidean signature in quantum field theory, this is e to the minus something. Like the Euclidean action is bounded below in quantum field theory. You get like e to the minus d phi squared, etc. In gravity, it's not sign definite, even in Euclidean signature. So there's and it's also not renormalizable. Now, you can still make sense of it by doing something like this and expanding it perturbatively. You can make sense of it by expanding it perturbatively. Some of the comments that I guess, some of the things I'm saying also apply to quantum field theory. That we don't really have, in many cases, essentially any interacting case, a definition of the quantum field theory path integral. What we really do in quantum field theory is we expand stuff in perturbation theory.
Well, unless you're doing like lattice gauge theory, then you.
Well, then you're not doing this path integral. Then you have to explain how that's the same as doing the continuum path integral. So it's but gravity's a bit worse for these two reasons. First of all, it's not renormalizable. Now, there are lots of quantum field theories that are not renormalizable. It's similar in that sense. But secondly, it has this issue with the Euclidean action, which people play tricks, they rotate contours, they try to make sense of it. But as long as you're just expanding in perturbation theory, it doesn't really matter. Since that's what we're going to do anyway, we're not really going to worry about it. Yeah.
So we know that all degrees of freedom for the metric are not physical, right? So we need to do some kind of a gauge fixing.
Yeah.
So I was thinking, like, if you do the gauge fixing and then you get the gauge fixed action and then expand that in saddles, so how do you know that that yields the same saddles?
I think aren't the saddles of the gauge fixed action going to be the same? Let's see. Well, first let me tell you how we do this in practice, and let's see if this answers your question. So in practice, we solve the classical. We don't worry about gauge fixing in the first step. In practice, we solve the classical equations just by writing down the Einstein equations, maybe coupling to fields. We find a solution of the classical equations. And then we take our action we take our action here and we expand it around that classical solution to some order. Now that expansion will have gauge fixing issues that we have to worry about, because like when you look at, for example, the h mu nu, the metric perturbation in that expansion, you're going to have to worry about gauge fixing to calculate that's the graviton, and you're going to have to worry about gauge fixing to calculate the graviton contributions. So what we do in practice is we solve the classical equations, we expand out, and then it's only when you start talking about the fluctuations that you have to address this gauge fixing issue. And I think that's generally the correct way to do it.
I see. So the issues are in the subleading terms.
Yeah, the gauge fixing only shows up when you start talking about it only is an issue that you have to worry about when you start talking about the quantum corrections. Other questions?
Are the boundary conditions for phi fully specified if you don't know the manifold?
For phi, you said?
Yeah.
You know, I should have mentioned that we also have to specify boundary conditions on phi. I didn't say it because those are just like the usual. We always have to do that on all the other fields. So usually we impose like phi goes to 0, and then we're done dealing with phi. Okay. We're going to, well, for now, let me talk about cases where the matter fields are 0 on the saddle. So we're expanding around a solution that's purely gravitational. This will include a Schwarzschild black hole. It does not include, say, Riester-Nordström, where you would have to also turn on gauge fields. But it won't change very much. This will just let me write some things a little easier. Then the gravitational path integral z of beta is approximated to leading order by e to the minus Euclidean action. Okay, so this is the leading term. It's the classical contribution at order 1 over g Newton up in the exponent. Where g bar mu nu is a solution of the Einstein equations with ds squared goes to a cylinder, d tau squared plus dx squared plus dot 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 with tau equals tau plus beta. So, do you know any solutions like that? Yes. So we do know a solution like this. We discussed, it's the Euclidean Schwarzschild black hole. Okay. So the asymptotics here are that we have a circle, and we're filling it in somehow. It's up to gravity. In this case, in the semi-classical approximation, it's up to classical gravity how to fill in the rest of this geometry. But we've already learned how to do that because we said that the Euclidean Schwarzschild black hole has exactly these boundary conditions. So g mu nu bar is the Euclidean Schwarzschild solution, which, recall from a few lectures back, was this cigar geometry, which far away from the black hole has a cylinder of size beta. This is at r goes to infinity. but caps off at the Euclidean horizon, r equals 2m. And r is the direction along the cigar. Tau is the direction around the cigar. This is the saddle point that dominates this integral. This is it obeys our boundary conditions, it solves the Einstein equations. So this is what we want. So what do we learn from this? Well, we learn the partition function. We learn the partition function from the Euclidean action. And if we phrase this in more thermodynamic-y language, what we learn is the free energy. So recall the free energy in thermodynamics is beta F is equal to minus log of Z. And we've just concluded that that's equal to the Euclidean action, i.e. on G bar. So, well, usually we call F the free energy. So the conclusion is that free energy times inverse temperature is the Euclidean action is the on-shell action of the Euclidean black hole. So we're now going to calculate that, and it's that calculation that's going to give us some confidence that we're on the right track and that this definition makes sense, because actually we already know the free energy of the Schwarzschild black hole. We calculated the energy, we calculated the entropy, we calculated the temperature. We already know that F is equal to the mass minus temperature times entropy. So we're going to do this calculation now of the Euclidean action and confirm that it agrees with thermodynamics. Yeah.
How do we know that this is the only saddle point?
Sorry?
Do we have to check that like this is the only saddle point?
Yes, we do. Good. So this is a contribution to the partition function. But we should worry about whether there are other saddle points. And in asymptotically flat space, I think that, as far as I know, there are not. But like in anti-de Sitter, there are, and we have to include them and sum over them. Yeah.
Just like a trivial space at a finite temperature.
That's true. Yeah. Yeah. Sorry. I guess even in flat space.
Wait, doesn't that have the wrong boundary conditions then?
Well, I think he's talking about the cylinder. So the cylinder itself is flat, and therefore satisfies the Einstein equations. Yeah, sorry, I misspoke. There's a cylinder. That also contributes. And what we should do is we should sum over them, and they're both included. And
That formula is not exactly right.
well, this formula is extremely close to being exactly right, because when you have a sum of exponentials, and you take the log, you really just get the dominant term. This is usual thermodynamics. Okay, so this formula is right if you're in a phase where the Schwarzschild black hole dominates the sum. Is the dominant, so there's a dominant saddle point, and there could be phase transitions as you tune the temperature where they exchange dominance. But in the black hole phase, this is the formula for the free energy at leading order. There are non-perturbative corrections coming from the subleading terms. Yeah.
Do other kinds of black hole solutions also contribute?
It depends on your matter theory. Typically no. Like the simplest answer is no. So like for example, the Riese-Nordstrom does not contribute because to the calculation we're doing now, because the boundary condition we're putting on the matter fields is one that would correspond to not having any chemical potential at infinity, and therefore not turning on any charge. So the Riese-Nordstrom would not obey our boundary conditions. Now, you could ask if there's a solution with like some scalar junk or something turned on deep in here that does obey our boundary conditions. Quite often the answer to that is no. This is the no-hair theorem of general relativity that says that under certain conditions, there are no solutions that look like black holes with extra junk, hair. Okay, so the no-hair theorems apply only in special circumstances. There are cases where you can have hair. And in that case, you have to worry about that, and you have to include the possibility. You have to include that in your sum and look for other saddles and ask whether those can compete with the saddles that you found. Yeah.
What about Kerr?
What?
What about Kerr?
So Kerr, the rotating black hole, also doesn't satisfy our boundary condition.
Okay.
So the rotating black hole has a 1 over r d tau dx term. It might be r squared, I can't remember. It's probably r squared. Well, it's d tau d phi, really. 1 over r to some power, d tau d phi. And when I said dot, 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 I was a little sketchy about what I meant by that. But in particular, I'm disallowing any terms that look like this.
Even though it dies off?
Yeah, exactly. The dot, dot, dots are not just any old things that die off. They have to die off fast enough. So we get to specify how fast we want the other stuff to die off. And if we allow this term to be here, so we could do different boundary conditions where we declare that we want that term with some coefficient. And that would correspond to doing a calculation at angular potential omega. So by setting this term to 0, I've imposed that I'm doing the calculation at finite temperature beta, but at 0 angular potential, so the Kerr black hole doesn't contribute. If I turn on the angular potential, then it will. Okay.
Wouldn't other problems arise though? Like the problems that like Kerr can't have a, like how am I supposed to think of like a thermal partition function for Kerr? If thermal Kerr doesn't even make sense.
Yeah, there's issues with defining the quantum fields on a Kerr black hole. Those will not show up in this approximation. This is an approximation. This is just a leading term, the classical term in this approximation. If we started calculating the corrections around Kerr, we would get in trouble. And there really isn't a good saddle point for Kerr that makes sense once you start including the corrections, unless you put the whole thing in a box and worry about stuff like that.
I think this may be related, but how would you do the analytic continuation of the Kerr vector for the d2 d5 term?
Yeah, the Euclidean, so the Euclidean Kerr metric, there's an I here. The Euclidean Kerr metric, the simplest way about thinking of the Euclidean Kerr metric, there's an I here because when you Wick rotate to Euclidean, this comes with an I. But that's actually okay. It's actually okay to use a complex geometry. You know, I've discussed I've discussed path integrals on real geometries to prepare quantum states. But a path integral on a geometry like this, which is complex, also prepares a quantum state, and it's actually okay. So you can do that.
So the metric is allowed to be complex?
Yeah, the metric is allowed to be complex. Well, it depends. There are cases where the metric is allowed to be complex. I wouldn't say that we've made sense of it in general when it's complex. Most of this stuff we have not made sense of in general. But for Kerr, it's fine. To be safe, I'll stick with that.
Where do you specify in the integral whether you're integrating over complex metrics or real metrics?
It's part of the contour of integration. So
Okay.
there's a contour of integration in the space of metrics. And we have to choose that contour. So we not only pick boundary conditions, we pick a contour. Okay, any other questions?
I have another question. I mean, this is something that we talked about a while ago when we were talking about black hole thermodynamics, but we consider the energy of the Schwarzschild black hole to be M, even though it's a vacuum solution. And so that's a little odd to me. Like, in what sense does it have energy M?
Well, in every reasonable sense. I mean, the gravitational field itself can have energy. Same is true of the Maxwell field. You know, you can have solutions of the Maxwell equations, the vacuum, what is it called? The vacuum Maxwell equations with no charges or anything. You can have solutions of those equations which nonetheless have energy. And this is not so different. The metric itself is carrying the energy.
But isn't the stress energy tensor just zero everywhere in the Schwarzschild black hole?
Yeah, T mu nu, every time we talk about T mu nu in GR, this is just the matter contribution to the stress energy tensor. And you cannot think of this as something that you can use to calculate the energy of a gravitational background with fields on it.
So how do we know what the energy of the gravitational fields?
Well, there are methods to do this in GR. Basically, you have to calculate the Hamiltonian. And it's known how to do that. What you get you get integrals that involve not only the matter stuff, but also the metric stuff.
Yeah, I remember
And-
we did this in GR too.
Yeah, we
Okay,
did, yeah.
okay.
Okay, so the next thing I'm going to do is to do this calculation. I like drawing pictures. In QFT, I could get away with this because I assume you've seen a lot of QFT. But this is a little different. So we're going to have to do the actual calculation. And what we're going to do next time is to calculate this on-shell action and make sure that it makes sense with thermodynamics. But I don't want to start this in the last 30 seconds, so let's stop here.